In this video, we're going to look at a different form of how to express complex numbers. We've already seen two forms of a complex number in first year, so we can write it in the Cartesian form, which is like x plus yi. And we can also write it in the polar form with r's and theta's. The form that we're going to look at is called the exponential form. Let's just have a quick look at where this comes from. And it's a nice little recap of some of the series expansions from first year. So if you think about these series expansions for e to the x, sine x, and cos x, let's see what happens if we substitute x equals I theta into our e to the x expansion. So we've got e to the I theta. That would be equivalent to, maybe pause and sub in and see what happens into this expansion. So we'd get 1 plus I theta plus I theta squared divided by 2 factorial, which is 2, plus I theta cubed divided by 3 factorial, which actually, you know what, I'm going to leave it in factorial notation because we can still leave it like this. We'll still be able to see what happens. I theta about 4 over 4 factorial, and so on. We could get a few more terms, but I think this should be enough for us to visualize what happens. Okay, so let's just focus on these brackets, and remember I squared equals minus 1. I cubed would be I squared times by I, so that would be minus I, and I to the power 4, we're back to 1 again, because remember the powers of I form a cycle, don't they? You've got I minus 1, minus I, 1, and the powers of I would always repeat in this cycle of period 4. Okay, so we've got 1 plus I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial plus I to the power 4, which is 1, so theta to the power 4 over 4 factorial. And if you look at what we've got here, this expression, this infinite expansion, we've got some real terms and we've got some imaginary terms. So if we just focus on the real terms, look at what we've got. We've got 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial. Essentially, we've got cos theta, haven't we? Because cos of x is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. So this e to the I theta, part of that expansion for e to the I theta would contain cos theta. Let's focus on the imaginary components. And we've only got 2 of them, but there would be more, wouldn't there? It's just an infinite expansion, it would keep repeating. And so the powers of theta would keep increasing, we get some real coefficients, some imaginary coefficients. But we've only got 2 of them. Maybe if you write a few more down, it'll be easier to see. But look at what we've got. Sine x is x minus x cubed over 3 factorial. So we have got x minus x cubed, theta minus theta cubed over 3 factorial. The next one will be plus theta to the 5 over 5 factorial. So we've got this sine x expansion, but all the terms have been multiplied by I. So this e to the I theta is made up of 2 parts. It's cos theta plus I sine theta. Okay? So essentially this is going to be really important in this topic that we're going to be moving on to. We know that if we had e to the I theta, that would be equivalent to cos theta plus I sine theta, and this is going to allow us to think about how to write a complex number in exponential form. Okay, so I think we should probably try and visualize what's going on here without getting lost in the algebra. If we think about our complex plane, and we've just got a general complex number, x plus iy, so obviously we've gone x across, we've gone y up, and that's probably what we're most familiar with, like our x and y coordinates. You've got your real axis, you've got your imaginary axis. Last year we also looked at how to write it in r theta form, in polar form, and we should remember this just comes from a little bit of trigonometry. This x coordinate here, we know is, because it's adjacent to the angle theta, we could write it as r cos theta. And the y coordinate is opposite, so we could write it as r sin theta. Just comes from Sohcahtoa, you know, sine is opposite over hypotenuse and then we multiply off. Okay, but you'll see a lot of this. You should just be comfortable to split this up into its two component parts. If it's adjacent, we use r cos. If it's opposite, we use r sine. Okay, so we essentially now know that we could write x in Cartesian form. We also know x is equivalent to r cos theta. We know y is equivalent to r sin theta. And if we take a factor of r out, does this look familiar? Cos theta plus. I know I'm a little bit inconsistent in where I'm placing I normally write it at the end, but when I'm working, but I suppose in this identity it is written at the front, so I should write it at the front. So Cartesian form, we know about polar. We know x is r cos theta, y is r sin theta. Now we've got it in this form, and we also now know that cos theta plus I sin theta is equivalent to e to the I theta. So that is the exponential form of a complex number, where r represents the magnitude, the distance from the origin, and theta represents the argument, or remember the angle. Theta has to be measured from the initial line, from the positive x-axis, or from the positive real axis, I should say. So theta is measured in that direction. Okay. Okay, so let's try example 2. It says express in exponential form, and we've got a couple of complex numbers. You definitely want to draw a sketch while you're doing this. Okay. You can draw a full axis if you want, because that's your real axis, that's your imaginary axis, or you could just draw an initial line like this if you're thinking about it in polar. I suppose I'm going to use a real and imaginary axis. Okay. So we've got 1 plus root 3i. That distance is 1. That distance is root 3. Remember, all that we're doing is thinking about a right angled triangle. So if I want to write it in exponential form, I just need to figure out what's the magnitude, what's the argument. Okay, just like we did last year. R would equal the square root of 1 squared plus root 3 squared. So r would equal 2, and the argument, theta, we can, with a bit of practice, you should spot this, because there's a very common ratio that always comes up. Technically, you should know these ratios already. You know, but if you're working with tan, because tan is opposite over adjacent, you could just look at that and say, well, tan theta equals root 3 over 1. You also know that the hypotenuse is 2. So if you're more familiar with sine or cos, you can think about it as sine. Sine is opposite over hypotenuse. So if sine theta is root 3 over 2, we should know that theta is pi over 3, or 60 degrees, but obviously we're working in radians. If you're not sure, you can just say tan theta equals root 3 over 1. Solve, you'll end up with theta equals pi over 3. Okay, so therefore 1 plus root 3i would be the same as 2e to the I pi over 3 in exponential form. Next one is 2 minus 2 root 3i. This is where you'll see the sketch is really important. So with 2 across, 2 root 3 down. The actual argument that we need to use is this, all the way around. But we can obviously look inside the right angle triangle and find this angle. And the magnitude would be the square root of 2 squared plus 2 root 3 squared, which would be the square root of 4 plus, if I square this, root 3, square this 3, so we've got 3 times by 4, which is 12, so we get root 16. Again, with practice, you may notice that this triangle here, 2 and 2 root 3, we're just thinking about the distances, it's just a scaled up version of 1 and root 3. So if the original, this one had the magnitude of 2, obviously this one's going to have the magnitude of 4. Okay, and again, also if you notice that that's a similar triangle to the one that we were working with before, if that was 1 and root 3, that angle there was pi over 3. So if I've got 2 and 2 root 3, guess what, that angle there is also going to be the same ratio, isn't it? So it's going to be pi over 3. But again, just use tan or sine or cos if you want, but we'll end up with theta equals pi over 3. And be careful here, actually, that's not my answer, is it? We've got 2 options now. We could write it as minus pi over 3, because we could, if you do minus, you go in this way, aren't you? You're going clockwise. Or you could write it as two pi and then minus the pi over 3, so that would be 5 pi over 3. And sometimes in the question it'll specify like what your argument needs to be between. It might be between 0 and 2 pi, or it might be between minus pi and pi, so you could use either one depending on what the question says. And this one doesn't specify, it's just about getting used to the form for the complex number. So I'm going to write it in the form for e to the minus pi over 3i. Okay, so for this one again, sketch should be useful. Minus 5i. Hopefully we're okay at spotting the geometry of this. We've got a nice isosceles triangle, haven't we? If that's 90, they're both 45s. In other words, if that's pi over 2, we know that's going to be pi over 4. So the argument that we use will be pi plus pi over 4. So we could write it as 5 pi over 4. Alternatively, you could write it this way, and it would be minus 3 pi over 4. And then r, if we just do Pythagoras, square root 5 squared plus 5 squared, which ends up being root 50, which is 5 root 2. Okay, so therefore, minus 5i would be equivalent to 5 root 2 e to the 5 pi over 4 I. Part D gives us, it's in a slightly different form, but essentially remember if it's written in this form, we know that this 4 is the magnitude and this 2 pi over 3 is the argument. So you can draw it out if you want. I mean, you don't need to draw this one out, but just to think about what's happening. 2 pi over 3, it's like 2/3, isn't it, of pi. You think about, if you're more comfortable with degrees, don't forget if that's 180 degrees, 2/3, that would be 120 degrees. But try and get used to thinking about it in radians. And that distance there would be 4. Okay, so clearly the complex number I'm looking for, the real part is going to be negative, the imaginary part is going to be positive. Okay, and so there's a couple of ways of doing this, but I suppose the easiest way of doing it is to just use your calculator to evaluate what cos of 2 pi over 3 is and what sine of 2 pi over 3 is, and then that would literally just spit out the Cartesian form. Oh no, actually we don't even need to do that. It says express in exponential form, doesn't it? Read the question, Josh. So we know that r is equal to 4, and we know that theta is equal to 2 pi over 3. That's literally all we have to do. So therefore, for e to the 2 pi over 3. That's it, straight away into exponential form. Okay. Exponential form of a complex number is actually really useful because we can use it to quite easily manipulate like powers of complex numbers. Like imagine if you were trying to do 1 plus root 3i and you're going to raise that to the power of 10. Obviously you don't want to expand the bracket out because that would be a nightmare. But you could write it in exponential form and then raise it to the power 10 because it's, you know, it's really easy to write 2e to the, what would that be, 1 across root 3 up, so pi over 3. If I was going to raise that to the power of 10, then think about the indices where 2 to the power 10 and e to the pi over 3. If you raise a power to a power, you just multiply them together. And you would get a relatively large number, obviously. I just made that question up. Okay. You can also divide complex numbers really easily, and we'll see that in the last part of this question. So the last part says, hence, evaluate 1 plus root 3i divided by 2 minus 2 root 3i. Now you did this last year. We have looked at how to divide complex numbers and multiply complex numbers. If we were doing this last year, what we could do, it's a nice recap, is you want to multiply the top and the bottom by the conjugate of this. So we'd multiply by 2 plus root 3i, 2 plus root 3i, and when we do that, the denominator would become real because you get 2 times by 2. The bits in the middle cancel out, plus minus, and then you get this times by this, and because you have I squared, it becomes real, so we end up with a real number on our denominator, and then we can just tidy up and get it into a Cartesian form. But let's think about it in exponential form instead, because maybe it's a little bit quicker. So if I was trying to do this divided by this, we've got 2e to the pi over 3, I divided by 4e to the minus pi over 3i. So 2 divided by 4, it would be a half. When we divide, we subtract the powers, don't we? So minus the minus, it becomes pi over 3i plus pi over 3i. So we could write it in exponential form. And obviously if the question said, write it in Cartesian form, once you've done your divide with your exponentials, you could then just go back to, oh I know, e to the I theta, actually I'll show you that. So we could also write it in Cartesian form if we were asked. So remember, e to the I theta is cos theta plus I sin theta, so that would be the same as cos 2 pi over 3 plus I sin 2 pi over 3. And then obviously you can use that, your graphical calculators, and just make sure you're in radians, and you could write it in Cartesian form. So cos of 2 pi over 3 would become minus a half. Sin of 2 pi over 3 would be root 3 over 2, so we'd end up with minus a quarter plus root 3 over 4 I. Okay, so we've got to get used to the different forms of a complex number, because depending on the question, it might be easier to work in exponential form, it might be easier to work in r theta form, it might be easy to work in Cartesian form. But what we're going to be moving on to next, we're going to focus a lot on this identity. Okay.